first slide here, the hottest matter. And of course, a term like that, well, what does it mean? There's limits, there's caveats to everything, right? So here are three things that are hot. A hot day, like today, molten rock, lava, about 2,000 degrees. Center of the sun, 28 million degrees. These are all hot in their own spheres. The hottest thing that you can actually find if you just look around the universe is the centers of supernova. And this one rings in at about 150 billion degrees Fahrenheit. But what I want to tell you about today is the quark-gluon plasma. We don't have a picture of it. I'm going to try to explain, give you a word picture of it. But it's something about 5 trillion degrees Fahrenheit. So this is really hot. It's the hottest matter that exists in nature. This is the temperature of the universe just a few millionths of a second after the Big Bang. So this is hot not only on a relative scale, but on an absolute scale. So we're going to start with the nucleus. And you guys are physics undergrads and students, so of course you know that the nucleus is the center of the atoms, and it contains almost all of the mass of the atoms. You know that it's composed of a collection of protons and neutrons. This is my generic nucleus of protons and neutrons. And these nucleons are held together by the strong force. And maybe I don't remember everything about what it was like to be a student, but what I do remember is sitting in a chemistry class and someone asked what holds the protons and neutrons together in the nucleus, because you would think from the electrostatic force they should just fall apart because of all the positive charge in the protons. And the chemistry teacher said, "That's nuclear physics, we're not interested in that." We are interested in that here. This is what I do. The strong force is, of course, one of the 4 fundamental forces of nature. There's only 4. This one is the one that I studied. And it seems kind of stupid to write this, but it's characterized by strong, short-range interactions. They're short-range, they're often found within the nucleus. They're strong, it's the strong force. So what's inside these protons and neutrons? It's kind of a black box, maybe, to an undergraduate physics kind of outlook. This is sort of the classical picture of a proton or neutron. It doesn't really matter. It's 3 quarks illustrated by these balls, held together by gluons, which bind these things together. Gluon's not a terribly original name. The quarks, instead of carrying they do carry electrical charge, but they also carry color charge, and that's the charge of the strong force. And the gluon is what mediates it, but you see in the difference from E and M, the gluon actually carries the color charge as well, and that's what's illustrated by these diagrams here. So the valence quarks define what kind of hadron you're looking at, what kind of proton or neutron. Of course, there's also a sea of virtual quarks, antiquarks, and gluons that really fill this in. And so this is a classical picture. There's no good picture that has all of the little interactions that generate this sea. But what's interesting about the strong force is one of its defining properties is confinement. These quarks and gluons are bound inside color-neutral particles. All the color is stuck inside the proton or the neutron, whatever you have. You don't get a free quark, and this is what makes the strong force actually very hard to study, because the details of it are really locked up inside these very small things, which are tightly bound together. So how are we going to study this? And the way that we do it in heavy ion physics is to look at the strong force at very high temperatures. We want a system that's hot and dense enough that the quarks and gluons don't have to be confined anymore. This is really the central overriding goal of heavy ion physics, which is what I do. So you take the nucleus, these many protons and neutrons stuck together, and you add a whole lot of energy to heat it up. Now, where are you going to get that much energy on that small of a scale? The nucleus is a few times 10 to the minus 15 meters across. How are you going to do this? Well, the solution is actually to get 2 nuclei and smash them together. So you have then something, as you smash them together, that has a lot of energy in a very small system. And this is the means that we use to create this system of deconfined quarks and gluons, and we call it the quark-gluon plasma. It's just words. So how do you do that? How are you going to smash together 2 nuclei and measure what comes out? Well, you do it in particle accelerators, and some of you are undoubtedly working at RHIC, which is the one that's here. You can go out and see it. We're in the physics building, which is right here, and in the woods here is the RHIC accelerator. There's another one in Geneva, the LHC, which of course you know from its high energy physics program. It discovered the Higgs a couple of years ago, and they continue to do very exciting stuff. But they also have a heavy ion program. So at 2.76 TeV, which is just a unit of energy, they collide lead nuclei together. And at a lower energy at RHIC, we collide mostly gold nuclei together. So these are the facilities where you can collide nuclei together, very high speeds, and create and study this system that I've been telling you about. So if you imagine you have this matter and you want to study it, right? So there's no picture of the quark gluon plasma, so I made a PowerPoint circle. This is the quark gluon plasma. What would you do to it if you could study it? Well, you might shake it, you might apply a temperature gradient and see what happens to it, you might scatter things off of it, you might do a lot of things. But the problem is it's a nuclear scale. So it lasts for what, a billionth of a trillionth of a second before it just expands and cools off into normal matter. And it's a billion times smaller than the pixel on your iPhone display, so you can't see it with your eyes. So when these two individual nuclei collide, they create one droplet of this matter, and this process happens thousands of times a second at these colliders. So it's not something that you can react to. We can watch what comes out of the collisions, but we can't do anything to it ourselves. We can set up the collision, watch what comes out, but everything in between is something that we have to infer. And as an experimentalist, this is, I think, what makes it exciting, because it's a big puzzle. So what do we actually see when these collisions happen? Well, hundreds or thousands of new particles are created in each collision. Right, we take the energy that we bring in and we turn it into particles. So this is a cute cartoon of just a bunch of particles represented by circles coming out of the collision region. So you can imagine two nuclei have smashed together head-on. They created something that's very hot, it's expanded, it's cooled off, and then it's created normal matter. So this is the matter that's made up of quarks and gluons bound together in these colorless states. And then these things, you know, they're on a scale that's a few times 10 to the minus 15 meters across. They fly centimeters, meters out to our detectors. And these particles and the correlations between them are really the only window that we have to what's gone on earlier in the collision. So we look at each collision individually, but we look at billions of collisions. So each one's a little bit different, and we look at as many as we can get our hands on in as many different ways as possible, varying the nuclei, varying the impact parameter, varying all sorts of things, to try to understand what happened in this inaccessible region that we think is so interesting. So this is an illustration, again, of Brookhaven, so we're down here, and it's a whole accelerator complex that creates, that is required to accelerate these nuclei to these high speeds, and then to smash them together. And then the collisions happen at two places at RHIC. One is the Phoenix experiment where I work, one is the STAR experiment where many people in this room work, and both of these collision regions have big detectors that are used to measure what comes out. So this is a picture of the Phoenix detector. It's the one from the first slide. It's the one that I work on. So the beams, this is taken apart. The picture when it's all put together and closed up really tight is perhaps not useful to look at. So this big green thing is our central magnet. And so a beam would come in from this way, gold nuclei would come in from this way, and they come in from this way as well where I couldn't draw an arrow. And at a time when we're taking collisions, this, and there's a mirror image that you can't see on the other side, these are detectors which measure the momentum and the energy of particles that come out, and they would be brought up very close into the magnet here. You can see how this kind of fits together. There's one on the other side, and so what do? You have charged particles, you put them in a magnetic field, you measure the deflection, and you know their momentum. In the back here, there's calorimeters that measure the energy of the particles. There's other detectors that help us measure what kinds of particles they are, pions, cans, and protons. You can read more about these, or people will be happy to tell you all about the details of these detectors. As you can see, of course, they're very complicated systems. It takes a lot of people and large collaborations to run these. So the particles then would come out here. Some of them would. They, of course, come out in all sorts of different angles, but a lot of them come out here and then hit our detectors. So what happens in a sort of schematic way when maybe you can see more about what is happening in this collision? You got a gold nuclei here, particles in the middle. This, of course, is not to any reasonable scale. These are what's coming out afterwards. So what does it look like in a detector? Well, this is an event display from the STAR detector. So it's got the same orientation as the previous slide, nuclei, nuclei. And all of those tracks represent particles that were detected in one single collision. So this is a head-on gold-gold collision. So the nuclei mostly overlap, and they create a lot of particles. You can create thousands of particles in a single event. So if you turn it around, you rotate it at 90 degrees, so the beam would come either both into and out of that circle there. And so you can see the particles come out in all different directions, which makes sense because there's no preferred direction necessarily coming in, so they have to come out in all angles when they come out. So what happens? I mentioned a couple of times the impact parameter or the overlap between these two nuclei. And while you think of nuclei as impossibly small, they're on their own scale. You can define an impact parameter. There can be collisions where the nuclei completely overlap, and collisions where the nuclei barely interact at all, where they mostly miss each other. Actually, we can measure that. That's pretty interesting. So if you take the view of the same one that I showed in this event display over here, so you have a nuclei coming in and a nuclei going out of the screen, then we vary the impact parameter of these nuclei. Now, what I've shown here, I want to walk you through one of these plots. So you can see that there are circles. There are some that are blue and there are some that are red. Blue is one nuclei, red is the other. So one's coming in, one's going out. It doesn't actually matter which one. The shaded nuclei that you can mostly just see as black circles, black open circles, those are the nuclei that didn't participate in the collision. What happens? They miss anything from the other nuclei, and they essentially just get shaved off and continue forward. The nuclei that are shown as solid circles, those are the ones that interact. So this is a single collision. And so you can see that the region where the nuclei overlap, it has a shape. And by varying the impact parameter of these nuclei, you can change the shape. Here the centers of the nuclei are far apart, and here they almost completely overlap. This is the kind of collision which would lead to a display like that one that I showed you above. So you can change the shape as you change the impact parameter. And one thing that I also want to draw your attention to is that the nuclei, so these are Monte Carlo simulations of the nuclei, the protons and neutrons in the nuclei have been distributed according to a Wood-Saxon distribution. And you can see that the positions fluctuate. There's a probability distribution associated with where these nucleons are. So each one's a little bit different, they're unique. So you get something that's mostly elliptical here, something that's more round here, something that is the first order completely round and doesn't have a preferred direction here with zero impact parameter. So that is the parts that don't interact. So what might you do? Well, if you can measure the orientation of this, which we can, then you can start to count the particles with respect to this angle, which I've just called it phi here. It's a good angle. And so if you just count the particles that come out with respect to this angle, this is what's shown here. This is actual real data. It's from the ATLAS experiment. Left out the reference, unfortunately. So if you count the number of particles, you see that more particles come out at 0 degrees and pi. You can see there's a symmetry between 0 and pi. Then at minus pi over 2 and pi over 2. And so those are the long way out. You get more particles that come out this way than come out this way. And it's actually pretty substantial. It's something, about a 20% difference. So what if we just forget about the nuclei and we just leave the shape here for a second? So you get less particles there, and more particles come out this side. So what does this tell us? Right away this tells us that interactions are important. If you have you pretend this is the outline of your quark-gluon plasma your overlap region where the nuclei have interacted, and you just have a few particles and they fly out, then there's nothing to convey anything about the shape of what happened to the final state, to the particles that you measure with your detector. This particle can fly out in almost any direction, and it's not going to run into any other particle. It's not going to tell you anything about what's going on. It's not going to find out much about the rest of the system. Now, if you start filling it in with more particles, and you imagine your system then becomes more dense, then of course it's more likely to hit something else. It's more likely to know about other particles that are also part of the same system. What we have in the quark gluon plasma is actually sort of an extreme limit of that. It behaves like a liquid rather than a gas. A dilute ideal gas, this is not. It behaves like a liquid instead. And so that's what I've attempted to draw with these gradients here. I don't know, my PowerPoint arc, you can think what you want of it. So what you have is you can think about pressure changes. This is a steep pressure change going out this way. And this is a more gradual pressure change going out this way. You can think about it as a mountain, right? This would be falling off the cliff to go this way, or this would be falling off the cliff. This would be walking down a slow path. So how do you characterize a liquid? If you want to think about it in terms of a liquid, then we have terminology that we begin to use to classify what this is. And one thing about liquids is they flow. So you can imagine a low viscosity liquid like water, where you can see the waves in Hawaii, which is very nice. You can think about a higher viscosity, which is something like honey, which is a very different sort of system. So we want to try to characterize the liquid quark gluon plasma. So the QGP flows well. You're able to transport information about the shape of the initial state to the particles that you measure in the final state, and it seems like it's a pretty strong effect, right? This is centered around 1, and so it's, say, 20%. So it tells us that this has a low viscosity. And we actually measure the viscosity by this parameter, which is called eta over S, which is the shear viscosity to entropy density ratio. And we measure it in these funny units, 1 over 4 pi. And so water has an eta over S of something like 25 in the units of 1 over 4 pi. The quark gluon plasma has an eta over S of something less than 5. So it's a very good liquid. It flows very well. So why these 1 over 4 pi units? Well, it's because there's actually a strength theory calculation that for a system there might be a universal minimum of 1 over 4 pi for this eta over S. So we want to understand, for this quark gluon plasma, which we went to try to explore the strong force, it seems that it's actually a very good liquid. Is it as good as you can get? Does it hit the bound? Is it close to the bound? Is the bound wrong? Does it go below the bound? This is a calculation. We're interested in measurements. I want to know what's going on. So quantifying this is one of the things that we're very interested in being able to do. So this is an important problem, and I want to tell you a little bit about how we've been doing it over the last couple of years. So you change the shape. So from these collisions with a large impact parameter to large to a small impact parameter, you change the amount of variation in the particle distributions. There's more variation here because this is less round. This is more round, and so there's less variation. So we want to be able to isolate the effects of the shape variations. And this is where the fact that we have both RHIC and the LHC with a factor of 15 difference in their collision energy actually helps us to do that. So if you just look at the number of produced particles in a collision, as you can imagine, those collisions where there's a huge overlap region, they produce more particles. More stuff happens, more things interact. So those are the ones that are nearly circular. As it becomes less and less circular, you're also going to a larger and larger impact parameter, and you're going to a steeper and steeper sort of almond shape with less particles produced. So this is sort of a generic correlation between the shape and the number of particles produced. However, if you go from RHIC to the LHC, you add more energy to the system. So that changes the number of particles produced because you just added more energy. So now you've shifted it. The same shape, different shapes have the same shape has different numbers of produced particles. So you change the collision energy by a factor of 15. We're looking at hotter quark gluon plasma at the LHC than at RHIC. So looking at the correlations between what we know about the shape and the number of particles that you make in these collisions is a tool that we're going to use to try to isolate the effects of the viscosity. So I need a little bit of math, but you guys can handle it. It's not a big deal. So we're going to quantify the strength of the modulation. And we're going to call it V2, just the strength. So a large V2 will be a large magnitude of this cosine oscillation. A small V2 would be a smaller magnitude of this oscillation. And if V2 was 0, you'd end up with the red dashed line, which has no modulation in it at all. So we're going to measure, this is an experimental quantity. So if you measure that at RHIC in the LHC, that's in purple at the LHC and in blue at RHIC, as a function, again, of this number of produced particles, this is V2. And you can see that at the LHC and RHIC, the distributions look shifted with respect to each other. So a large V2 is a collision where we think that it's dominantly, it's got a more almond-like shape, and a small V2 is a more circular-like shape. So we characterize that in terms of a quantity, the eccentricity. So you can define this eccentricity for any shape. If you have a line, the eccentricity is 1. If you have a circle, the eccentricity is 0. And everywhere in between, you can calculate it given a distribution. So if we take V2 and we divide it by this eccentricity, then we see that as a function of the number of produced particles, at RHIC and the LHC, the data that I showed you previously, which were shifted with respect to each other, when we divide by this parameter that we think describes the shape, they actually scale with respect to each other. They lie on top of each other. And I think this gives us confidence that we understand that this is a good measure of the shape, right? It relies on a model of what we think the nucleus looks like, but this gives me confidence that what we're doing makes sense. So there's a relationship between the geometry and the V2 is really a signature of the small viscosity of cork-gluon plasma. So then the question that I want to talk about that I posed in my title, and we can spend a while wandering around to get there, is really how small can the cork-gluon plasma be? The sub-question is, why is that an interesting question? So why take something that's so small and then try to make it smaller? I've already shown you that this is impossibly tiny. It's the size of a nucleus. Why would you want to make it smaller? Because you want to change the shape and the size to help measure the viscosity. By changing the size, you change the way the time evolution works. So if you take something where you have a big nucleus, two big nuclei smashing into each other, you'll end up with a cork-gluon plasma that's the size of the nucleus. However, one thing you could imagine doing is taking away one of the nucleuses and replacing it with just a single proton. And then if it's possible to create a cork-gluon plasma that's got a size that's on the scale of a single proton, then you'll make a much smaller one, and you'll have a different relationship between the size and the shape than you will with a heavy nucleus. So we've got into this business for heavy ion physicists and with big nuclei. But now I'm going to spend some time talking about very small things. So they took p-lead collisions at the LHC. I'm not sure, I'll get the date wrong, but they recently took p-lead collisions at the LHC, so that's where you have a big lead nucleus and a small proton that runs into it. And what they did is they measured V2, which was surprising that there would be a V2 signal at all. They saw this modulation in the particle distributions that I was telling you about. They were able to make an estimate of the shape and so this is V2 divided by epsilon 2 for proton-lead collisions at the LHC. And it's again as a function of the number of produced particles. But whereas the plot I showed you before went up to 1,000 in the number of produced particles, this plot is on a linear scale and it goes up to 50. So these are results from two different collaborations at the LHC from Alice and Atlas. And so you can see that V2 over the eccentricity of the LHC, it seems to be rising, general trend, and it's seriously non-zero, significantly non-zero. So now we're looking at big versus small collisions. What's going on? So we spent a while talking about these collisions which were large, which had a large eccentricity. These are these large overlap, or large impact parameter, heavy ion collisions. Now, if you replace one of the nuclei with a proton, then you don't need me to tell you that the first order, the overlap region there, is going to be circular. The proton doesn't really have a shape that I know much about. So the shape is going to be determined actually by the fluctuations in which protons and neutrons you hit in a lead nucleus. And you can model that, but you're always going to get something that's circular modulo some fluctuations. And so we went from something that was big with a large eccentricity to something which was small with a small eccentricity. So you have now two things that you vary here. You vary the size and you vary the eccentricity. So what other kinds of ways do we have to further constrain this? And actually, we have deuteron gold collisions at RHIC. So whereas why they took p-lead collisions at the LHC has something to do with the machine design, at RHIC we had not taken proton gold collisions, we'd actually taken deuteron gold collisions. And a deuteron is the next most complicated nucleus up from the proton. It's a proton plus a neutron. It's two nucleon system. And so if you take that and you smash that into a gold nucleus, then you end up with something that now has a large eccentricity and a size which is, well, of course, bigger than the overlap p-lead collision. It's still a lot smaller than when we were talking about heavy ion collisions, the collision of two heavy ions a couple minutes ago. So now we have something that's small with a large eccentricity. So then the question is does this scaling still hold? Now that's kind of an interesting technical challenge at this point, because which way does the ellipse go? We can't control this at all. What the orientation is, this is just the same picture. 3 different ways you can change the orientation. And we can't really measure that all that well. Of course, there's a resolution in how you measure anything, but this is a particularly tough thing to measure. And so we've got that here. So what are we going to do to try to figure out which way this went, or to get at these V2s? Well, you can actually use information from the collision itself. You can measure two particles. So the correlations between particle pairs. Now any particle in the event might not know everything about everything else that went on in the event, but it certainly knows more than you because it was there and you weren't. So we actually just look at the correlations between all pairs of particles in the event. So the precision is low, but obviously if you look at all sorts of pairs, then you have a lot of statistics to play with. Of course, as anybody who's ever done particle or nuclear physics knows, there's lots of reasons for particles to be correlated with each other. There's jets, there's decays from heavier particles, there's other things that can happen. So what we do is we've got an animation. So this is the signal. These are these events where we think the deuteron is really going through the center of the gold. So this is the signal plus background. It's highlighted in the red here. And our estimate from the data of what the background is. And so that, in this case, this is jets, particle decays, other correlations that aren't related to V2. That's what's shown in the blue line. So of course you can just take the signal plus background, subtract the background, and what you get is this. So this is now the correlation of particle pairs, and what you see, this signal minus background is shown in the blue, and what you see is that's actually well described by a cosine type shape. We see this cosine modulation that we saw back before for the particle distributions. So we've been able to do this without knowing anything about the orientation of the impact parameter, just information from the particles pairs that we see. So you can describe this, and this is actually related not to a single power of V2, but it's related to V2 squared, because you have the V2 of one particle and the V2 of the other. And so you can, of course, then use this to get the V2 that you're interested in. So that's what we did. So this is the same LHC plot that I showed you before, with the V2 over the epsilon 2, so the V2 over the shape variable. It's a function of the number of produced particles. And so you'd think that this V2 was really related to the shape, and that we were producing a quark-gluon plasma in these very small systems, then you should have the data from the deuteron gold collisions at RHIC lay somewhere in this band. Now this band is sort of sketchy, right? I've drawn this box with PowerPoint. There's of course uncertainties in the data. There's uncertainties in the theories of how well this would work. So I've kind of drawn a wide band here. It's an interesting thing to try to quantify how well we know this. So this is the data that we got from RHIC, shown here with this blue point. And you can see it actually agrees fairly well with the LHC data when you scaled it by the shape parameter. So this is interesting. Well, now what if you just take things a step further because you're a scientist and that's what you do? So now we take this data from not only the P-lead and D-gold data that I was just showing you, but now with the heavy ion data. So we put the plot back on a log scale, and it goes out to 1,000. And you see that if I took away the colors on these points, you'd be hard-pressed to figure out which point went with which data set. We really see a continuous behavior from systems that produce 10 particles to systems that produce 1,000. And I think that's pretty interesting. So that big, heavy ion collisions that we sent out to study, at the top, LHC energies, down to proton-lead collisions where not much happens, there seems to be a continuous behavior, and how this V2 relates to the shape of the overlap region. So these, of course, are the proton-lead and D-gold points here. These are the gold and lead points over here. There's a few points that overlap, the very peripheral lead points and gold points, where there's large impact parameters, so they have about the number of particles produced as in these smaller systems. And I think that's an area of very interesting physics, is to try to make more measurements there. But we see a continuous behavior here. Okay, so I think what I hope you've taken away from this so far is that the particle distributions that we measure reflect the initial geometry of the collision itself. We have something that works, that correlates the geometry to a measurement in big and small collision systems. And each nucleus is, of course, a little bit different, right? It's a quantum system, so you've got 200 protons and neutrons, and they move around inside the nucleus, and so each nucleus looks a little bit different. So these are just 3 arrangements of protons and neutrons and a single gold nucleus. Okay? So if you take 2 of those nuclei that have fluctuations and you start to collide them together, of course, they're going to look different. The ones I showed you before were nice distributions where you had almond shapes or circular shapes, but it doesn't take very long in looking through these Monte Carlos to find ones that look a little weird. Here, this is kind of almond shaped, but it's bent over. The impact parameter plane is here, but I would say the axis of the ellipse might be here. This one goes the wrong way, again, and it has these weird little islands. This one kind of looks like a bell. So each collision is unique. And remember, you, as an experimentalist, don't know exactly what the collision looked like, but the collision knows what the collision looked like. So I talked a lot about V2, which is really the ellipticity. But of course, there's all sorts of different higher order effects that you can look for. You can look for triangularity, the 4th order, the 5th order. So these effects are very clearly apparent in distributions that look like this. So we have this, we want to take this shape control a step further to really nail down what's going on in these small systems and to help us address the viscosity. Then, all right, so let's say we've gotten from a small epsilon 2 to a large epsilon 2 by adding a single nucleus. We've gone from something that's the 1st order circular to something that's 1st order elongated. So what if you wanted to play with this idea of changing the nuclear shape even more? Well, you might imagine trying to pick out the triangularity of what's going on. So a deuteron-gold collision has a small triangularity, right? It's a dumbbell. However, if you could get a nucleus with 3 nucleons in it, say 2 protons and a neutron, then you could, in principle, create a triangular-shaped quark-gluon plasma. This is especially interesting because these higher harmonics, the triangular shapes, the 4th order and the 5th order, these are particularly sensitive to the viscosity. So attempting to generate a larger 3rd order effect by creating a triangular quark-gluon plasma is very interesting to be able to constrain these viscosities. All right, so a triangular nucleus, of course, you can have them, right? So a deuteron is 1 proton and 1 neutron. Helium-3 is the next most complicated nucleus. 2 protons and 1 neutron. One of the great things about RHIC is that it's an extremely versatile collider. And so we had this idea to run these helium-3 collisions to try try to generate a triangular quark-gluon plasma. And we did it. Actually, the run finished on the 6th or the 7th, so just over a week ago. So now we have the deuteron gold collisions. We have helium-3 gold collisions on tape that are brand new, and they're being analyzed by me and other collaborators and colleagues. So this is, I think, very exciting. We have this data, and we're looking at it. The proton gold collisions at RHIC, we expect to take these data next fall. A long proton gold run, and then we'll really have the ingredients to explore this engineering the shape of the quark-gluon plasma. So I think that this is a really exciting time at RHIC, and this is something that the LHC, they can't do this. They don't have the running time, they don't have the flexibility, and so we will be able to do all of these at RHIC, and I think that this is very exciting. So I want to shift gears for a little bit. I've told you about a lot of measuring the correlations between particles to try to get at the viscosity. Now, if you had this quark-gluon plasma on the table, what's one other thing you might try to do to it if you were an experimentalist? You might try to shoot things into it and see how they scatter off the constituents. And that's another thing that I'm interested in, and I think it's a big step for the future. So this is an event display from the ATLAS experiment showing two very high energy jets. So if you're not familiar with these things, this is the beam's eye view. So you have a lot of energy coming out this way and a lot of energy coming out this way. So these are back-to-back sprays of hadrons. If you unroll the calorimeter, you can see them stick up. It's a tremendous amount of energy, and that's really the only thing that has happened in this proton-proton collision. Now, this is my cartoon version of a jet, so they're back-to-back, and they come out as hadrons. So pions, kaons, protons, neutrons, and they come out approximately back-to-back. Now, what if you were to take your quark-gluon plasma and put these jets in? Then you might have another way to address what's happening in the quark-gluon plasma on a different level. You're scattering these quarks and gluons that are scattered from the jets off of whatever is in the quark-gluon plasma. So they could bounce around by scattering off the constituents, that's what's shown by these little black lines, or they might radiate gluons as they propagate through, and that's what's shown by these purple lines here. So the jets themselves can be modified by the quark-gluon plasma. Instead of using an electron microscope or anything like that, you're using the jets, which are actually generated in the collision, as a way to probe the details of what's going on in the quark-gluon plasma. So this is an event display of jet quenching. So this is what it's called, where you have a jet that comes out. This is what we see. You have one jet that comes out relatively unmodified, and it's not balanced by a jet that looks like it. So this is the energy that comes out of the calorimeter towers, and you can see it's very high over here. And in this event, it's balanced actually by a lot of lower energy towers spread over a wide array, a wide range in angle. So this is from ATLAS. And so if you want to quantify that, you could actually look at the asymmetry between the jets. So these are jets where the two jets in the back-to-back system have about the same energy. And these are the ones where they have a very different energy. So it's just the asymmetry, the difference over the sum. So in proton-proton collisions, which is shown by these open points here, you can see that they're most likely to be very symmetric. What you see in lead-lead collisions is shown by these black points here, where you get a much reduced rate of symmetric jets. One of the jets has lost energy. Of course, as a physicist, you believe in energy conservation, so you didn't lose it. Where did it go? Well, finding the energy and figuring out where it ends up is the central question of jet quenching. And we're working on that at RHIC, and people are working on that at the LHC. And really the question is, where does it go? And what does it tell us about the matter we're studying? And so one of the things I'm really excited about is taking this detector, which I showed you here, the Phoenix detector, which you can see it's in pieces. It doesn't have completely cylindrically symmetric acceptance, and turning it into S-Phoenix, which is a new detector that we hope to build and take data with by 2020, 2021, that would be actually well designed to be a jet detector. Jets require really two things. They require large acceptance, that you can get both the jets, you can get the back-to-back jets, and they require high rates, because it doesn't finally these partons come in and exchange this much momentum and make something that really sticks out. And so that's what S-Phoenix is. It's high rate, it's large acceptance, and this is one of the things that I'm really excited about in the future. And so between RHIC and LHC, you change the initial temperature of the quark-gluon plasma. So it's not having these measurements in one place at one energy. It's being able to use these jets as you change what goes on in the collisions to figure out the details of what's happening with these jet measurements. And then it's taking it a step further. It's not measuring the jets and walking away. It's being able to figure out what the combination of these V2 analyses that I've been showing you, plus the jet quenching that I showed you a little bit of, and what does that tell us about how the quark-gluon plasma works? We're studying the same system in two different ways. So I think that this is a lot of where it's going. I think that this is an exciting field to work toward. So what we're really doing is, of course, exploring the strong force. We're creating a picture of the quark-gluon plasma by using the geometry variations of the collision of the nuclei. So the very small nuclei have surprisingly shown us that they can also produce a quark-gluon plasma, and I think this is interesting and will help us understand the viscosity better. And we're excited to be able to fully exploit this with really this complete program from protons, deuterons, to helium-3 or whatever. So, thank you.
Okay, do we have some questions for Anne? I don't see any hands up. Oh, okay, go ahead, Brian.
For epsilon 2,
Yeah.
is that something that you actually extract from a measurement, or is it calculated?
It's calculated. So what we do is we have a Monte Carlo, we distribute the nucleons in the nucleus according to, say, a Wood-Saxon distribution.
Yeah, I understand how you can calculate it.
Yes.
I didn't see how you can measure it.
No, you can't measure it.
And
So how do you do it event by event then?
Oh, well, we know what the distributions are. We don't do it event by event. We have the means of the distributions.
it's the mean V2 over the mean epsilon 2 as a function of the centrality,
Exactly.
or something.
Something.
Okay, yeah, Andre.
So there I have a naive question. So what drives the choice of nuclei? Why gold? Why not steel or something else?
So we wanted something that was big. That's why the RHIC program does gold nuclei. It's got 197. I was getting confused. It's 190.
They make nuclei around this size, right? Or is it easy to uniquely big?
What?
I mean, you have the entire periodic table there showing us.
So before they have a new source at RHIC now, so they have a wider flexibility. So that's what drives the uranium nuclei that they're able to accelerate now. But with the original source, gold was large and easy to produce in beam mode. And that's what drives the LHC using lead.
Why couldn't they use that?
So the original source that RHIC did not allow us to use lead. So that's what the difference is. But it's not a huge, between lead 208 and 197 for gold. Mike wants to make
So the
some.
lead they use at, so gold is also the stuff you buy in your wedding ring. If you have 24 karat gold, it's essentially isotopically pure. If you go get a lead fishing weight, it's not isotopically pure. To get isotopically pure lead, maybe lead 208, actually costs more per ounce than gold does. So.
I did not know that.
Any other questions? Yes.
Is there any theoretical prediction about the scale law between the A2 and A2?
Yeah, so there's a wealth of data. So there's a wealth of theoretical data, I guess. So the V2 that is compared to theoretical models which run relativistic hydrodynamics. A lot of the world-class ones are actually done by the theorists at Brookhaven. So they start with a model of the initial state of the nucleus, and they run relativistic heavy hydrodynamics, and they're able to predict the V2. I don't think I have a slide here, but they are able to get not only V2, but V3, V4, and V5.
Okay, I think they compare with the experimental data.
Yeah, they do compare with both RHIC and the LHC.
Okay.
And so that's really the tool that you use to extract the viscosity.
Okay.
What is the latest result for viscosity, or just did you give the final answer in your introductory slides already?
Well, so I didn't give the final answer.
Well,
So, all right, so it's depends on there are uncertainties, and so the interesting thing is that the viscosity seems to be lower at RIC than it is at the LHC. So it's certainly a few times this bound, sort of the ballpark number. But within a model, they get lower viscosities at RIC than they do at the LHC. And that is probably due to the fact that we're closer to the transition temperature, and the coupling is actually stronger at RIC, making the viscosity smaller. It's a better fluid. So that's another reason why it's very important to have measurements of both RIC and the LHC to really constrain the temperature dependence in this models. Now, of course, you don't expect viscosity to be independent of temperature, and constraining that temperature dependence, I think, requires real experimental and theoretical work.
Any other questions?
Yeah.
Yeah.
I'm thinking in this plot, the slope of the green and yellow points have a larger slope than the other curve.
That's why I think that, so there's systematic errors, which I've taken off for clarity, that shouldn't be taken off. There's another thing that I've mentioned briefly is that being able to push the heavy ion points from peripheral heavy ion collisions down here. So to be able to extend the purple and these blue points down so there's more overlap and be able to bring these up, I think is an interesting endeavor to try to figure out how different the slopes really are and to increase the region where they match.
Anyone else? Yes.
You just said that there is a lower viscosity at weight than at LHC. So is there like any particular energy in between where you have the lowest energy? I mean the lowest viscosity?
Well, so there's no way to realistically have collisions between the LHC energies and RIC energies. But what we are able to do is to take lower collision energy data at RIC and to compare that to these hydrodynamic models and to try to get a better understanding of the viscosity there. So that's something that's in its earlier stages, comparing the lower energy data at RIC to these hydrodynamic models. But I think that's a good way to understand more about that.
Okay, anyone else? If not, let's thank Dan again.